Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 9.7, and 9.7 is called Taylor Polynomials and Approximations. Alright, so first, let's get what the idea behind this section is. The idea is to find polynomials that approximate a non-polynomial curve. So what do I mean by that? So let's say that we have the following function, right? Something like this. Let's say that we have something like that, all right, where we have this asymptote here. Now this is clearly not a polynomial function because polynomial functions are defined for all real numbers, so this is not polynomial. But what we can do here is we can try to approximate this curve, right? And if you recall from Calc 1, there was something called linearization, right? Or essentially the equation of the tangent line. And what we did there was, well, we said we're going to fix a point and we're going to have a line, right? And that's fine as long as we're very close to the point of tangency, right? But that's just a tangent line, so we're approximating the curve with a line. Well, what we can say is, well, why do we have to use a line? Why can we not use a different curve? So for example, we're still going to have the point of tangency at the same spot, but we're going to say now, so around here, we're going to say, well, we can approximate this better perhaps with a something like this, with a parabola. And let's draw that better. So something like this. There we go. No, let's put that back. There we go. So there it is. So we approximate that better. Now, how is that better? Well, in here, well, we have a larger range overall where the value, the curve, is closer to the function, right? And we can come up with an even better approximation, right? If we have something like, so that was, instead of a line, we used a parabola. So that was quadratic. So instead of quadratic, we could use a cubic, and we can have something like this, right? Overall, yeah, let's make that look better. Make it look more like an approximation. Right, and again, we've got an even wider range. And then instead of a quadratic, perhaps, instead of a cubic, perhaps we go to a quartic. So in other words, fourth power, right? And it might look something like this. So we have an even longer range for where the function is similar, right? That curve. So that's the main idea. Well, the main idea here is we want to find these kinds of curves that approximate a curve better than a line, right? So that's our goal. The goal is to approximate a curve using a polynomial function. All right, so how are we going to do that? So to find a polynomial function, so to find this, to find the polynomial function P that approximates another function f, begin by choosing a number c in the domain of f at which f and p have the same value. That is, that p of c is equal to f of c. Right? What is this saying? What we're saying here is, well, we first must choose a point at which to approximate it at, right? When we did this with the tangent lines in Calc 1, well, we needed to find the tangent line at a specific point C, right? So we're going to be doing the same exact thing with these curves. We're going to be approximating them based out of our point of intersection there, based on C. So let's see. And by the way, this the approximating polynomial. Oh, that's how you spell approximating. The approximating polynomial p of x is said to be expanded about C, or centered at C. In general, I'll probably be using this a little more often, centered at C instead of expanded at C. Alright, but they mean the same thing. Alright, so now, how are we going to do that though? So let's see. We need to come up with we need to define something else here. So, definition. Taylor and Maclaurin polynomials. And well, what are they? So let's say if f has n derivatives at C, then the polynomial p sub n of x being equal to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c to the cube over 3 factorial, so on and so forth up until our nth derivative at c over n factorial times x minus c to the n. Alright, so that is called the Taylor polynomial of f at c. So that polynomial, so p sub n of x is called the nth Taylor polynomial of f at c. So that's what a Taylor polynomial is. If c is equal to 0, then we get the following. Then p sub n of x would be, well, let's see what happens. F of 0 plus f prime of 0. Let's make that f prime look better. F prime of 0 times x plus, and by the way, here we could technically say 1 factorial. Here we could, so I can just leave it as that, 1 factorial plus f double prime of 0 times x minus, assuming just x, right? X minus 0 is just x, so x squared. I'll write that as just x squared over 2 factorial plus f double prime of 0 times x cubed over 3 factorial, so on and so forth, until we get to the nth derivative at 0 times x to the n over n factorial. Alright, so in here, this is called, well, let's rewrite that. In here, p sub n of x is called the Maclaurin polynomial That's how you spell polynomial. What? There we go. For f. Alright? And essentially here, what I want you to notice the difference between these two equations. For these two polynomials, these definitions. The only difference is that wherever I have c up here, I have a 0 down here. That's the only difference. So what we can say here is that a Maclaurin polynomial is a Taylor polynomial centered at 0. Alright? A Maclaurin polynomial is a Taylor polynomial centered at 0. So now, let's find one. Find the nth Maclaurin polynomial for f of x is equal to e to the x. Alright? So, and I didn't want to do the nth. Let's use the fourth. The fourth Maclaurin polynomial for f of x equals e to the x. So, because we said it's a Maclaurin polynomial, what we're really saying is that our center is 0. So we have to keep that in mind. And let's see what is that we need up here. We need the function and we need a bunch of derivatives, right? So let's figure that out. So we have that f of x is e to the x. F prime of x is equal to e to the x. And how many times am I going to do this? Well, the nth polynomial, right? That's the last value over here, that n. In here, our n is 4. So we need to do this until we have 4 derivatives. So the second derivative is e to the x. The third derivative is e to the x. The fourth derivative is e to the x. Evaluating it at c equals 0, so I'm going to say evaluated at c equals 0, we get, well, e to the 0 is 1. So all of these are just 1, right? So at that point, well, what does that give us? Well, we can go ahead and write this idea, right? So it was the fourth polynomial, right? The fourth Maclaurin polynomial here is going to be, well, it was f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus the fourth derivative at 0 times x to the fourth over 4 factorial. And here, what is that? Well, we know that all these values evaluated at 0 were just 1. So I have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. Alright. Let's do another one. Let's say that I said find the Taylor polynomial p sub 5 of x for f of x equals ln of x at c is equal to 1. So we're centering this at 1. Alright, so how are we going to do this? Oh, let's not erase that. Well, we need to figure out a whole bunch of these derivatives. And how many? Well, right here. That 5 tells us that we need to take 5 derivatives. So the first derivative of ln of x is 1 over x. The derivative of that is negative 1 over x squared. The derivative of that is positive 2 over x cubed. The derivative of that, so the fourth derivative here, would be -6 over x to the fourth. Oh, we need to go to the fifth derivative. So the fifth derivative would be positive 24 over x to the fifth. All right, and now we're centering this at 0. So let's I'm just gonna shift this down a little bit. And since that was part of the instructions, oh, why is this bigger? There we go. I'll shift it down to there. Alright, so now we need to center this at 1, so I need to evaluate all of these at 1. So if I evaluate all of this at c is equal to 1, what do I get? ln of 1 is 0. 1 over 1 is 1. Negative 1 over 1 is negative 1. 2 over 1, 2. Negative 6 over 1, negative 6. 24 over 1, 24. Right? All I'm doing here is evaluating every single one of these at 1. So at that point, well, we're looking for our fifth polynomial there, so we know this is going to be so piece of 5 of x. Remember, it was f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial plus the fourth derivative at c times x minus c to the 4 over 4 factorial, and finally times the fifth derivative evaluated at c times x minus c to the fifth over 5 factorial, right? And well, what does that do for us? Let's see. We've got all these values. We evaluated them already, right? So we have 0. The first value here, that was 0 plus f prime of c. Well, f prime of 1 was 1. So we have 1 times x minus 1, right? Our c was 1. Plus f double prime of c. What was f double prime? Negative 1. So I have negative 1 times x minus c, excuse me, x minus 1 squared over 2 factorial. Plus f triple prime. F triple prime was 2. So I here have 2 times x minus 1 cubed over 3 factorial. Plus the fourth derivative. So negative 6 times x minus 1 to the 4 over 4 factorial. And finally the fifth derivative, which was 24. So 24 times x minus 1 to the fifth over 5 factorial. Expanding this a little bit, I'm just going to rewrite this now as that 0 is not really there, right? So it's going to be x minus 1 minus x minus 1 squared over 2 factorial plus 2 times x minus 1 cubed over 3 factorial minus. Actually, you know what? Let's think about this. What is 2 factorial? 2 factorial is just 2 times 1, so it's 2. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Why do I care about that? Well, here this 2 and this 2 cancel each other out. This 6 and this 3 times 2 being 6 cancel each other out. So we can say here is, well, this is just over 2. This part is just over 3. This next part is just going to be over 4. So I have minus x minus 1. Oh, let's go back to writing white. X minus 1 to the fourth over 4. And for similar reasons here, this 5 factorial, right? This 5 factorial is 5 times 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. So these 3 right here cancel out that 24. So I have plus x minus 1 to the fifth over 5. Cool. So now, these were just some examples in finding the polynomials, right? So let's actually use that to approximate some value. So let's see. So example C. Find the Maclaurin polynomial p sub 6 of x for f of x is equal to cosine of x, then use the approximation, or use the result, I should be saying, use the result to approximate cosine of 0.1. Alright, and this is 0.1. Alright, so let's see what we can do here. We're looking for the sixth Taylor polynomial. Excuse me, the sixth Maclaurin polynomial. And remember, Maclaurin polynomials were just Taylor polynomials centered at 0. So what we're going to do here is first find 6 derivatives. So I started with f of x being cosine of x. The derivative of that, negative sine of x. The derivative of that, negative cosine of x. The derivative of that. So the derivative of negative cosine is sine. The fourth derivative, so the next derivative, the derivative of that piece would be cosine. The fifth derivative would be the derivative of cosine is negative sine. And the sixth derivative, the derivative of negative sine is negative cosine. And well, since we're doing the Maclaurin polynomial, right, what we need to do here is we need to evaluate every single one of these at c is equal to 0. And what does that give us? Well, cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1 with a negative in front of it, negative 1. Sine of 0, 0. Cosine of 0, 1. Negative sine of 0, 0. Cosine of 0, 1 with a negative in front of it, negative 1. So what does that give us now? Well, what we can say now is that, well, what would our sixth Maclaurin polynomial look like here? Well, it would be f of 0 plus f prime of 0 times x minus, just times x, plus f double prime of 0, x squared, over 2 factorial. I'll do one more, f triple prime of 0 times x cubed over 3 factorial, so on and so forth up until the sixth, right? So plus the sixth derivative at 0 times x to the 6 over 6 factorial. And well, what would that give us here? F of 0. Well, we had 1. So we have 1 plus the first derivative evaluated 0. 0. So 0 times x plus the second derivative times x squared over 2 factorial. But what was the second derivative? Second derivative, negative 1. So we have here negative 1 plus the third derivative times x cubed over 3 factorial. But what was the third derivative? Third derivative, 0. Plus, well, the next one is going to be the fourth derivative times x to the 4 over 4 factorial. And what was the fourth derivative? 1. So, plus the fifth derivative times x to the 5th over 5 factorial. And the fifth derivative was 0. Plus the sixth derivative times x to the 6 over 6 factorial. And the sixth derivative was negative 1. And at that point, well, what do we get? Let's write it this way. So we have 1. This 0 goes away. Minus, right, because plus a negative. So minus x squared over 2 factorial. That 0 goes away. Plus x to the 4th over 4 factorial. That 0 goes away. Minus x to the 6 over 6 factorial. Alright. And there you go. That is our Maclaurin polynomial. Our sixth Maclaurin polynomial for cosine. And, but what did it say to do next? It said, use the result to approximate the value of cosine of 0.1. So let's see. So we're going to say here that cosine of 0.1 would be approximately our Maclaurin polynomial evaluated at 0.1. Notice that 0.1 It's really just 1/10, right? And in here, what do we get? We get 1 minus 1/10 squared over 2 factorial plus 1/10 to the 4th over 4 factorial minus 1/10 to the 6th over 6 factorial. And well, let's see what we get. 1/10 squared. 1/10 squared is 1/100th. So I have 1 over 100 and then over 2 factorial. 2 factorial is just 2. So 1 over 100 divided by 2 is 1 over 200. Plus 1/10 to the 4th. Well, that's going to have 4 zeros, so 1 over 10,000 over 4 factorial. 4 factorial was 24. So we're going to have really, that 4 factorial was 24, and then from here, 1/10 to the 4th gives us 4 zeros. 1, 2, 3, 4. Minus 1/10 to the 6th. Well, that's going to be 1 over 10 with 6 zeros. And then 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That is 720. So really here we have 1 over, well, 720 times 6 zeros. 1, 2, 3, 4, 5, 6. And at this point, if you plug this into the calculator and you plug it in there correctly, you will get that this is approximately 0.995004165. All right, that's what you would get out of the calculator there. Now, if you were to plug in cosine of 0.1 into the calculator, you would get the output of 0.995004163. Oh no, yeah, 1653. So in here, what we saw was our approximation is just as good as a calculator approximation. All right, in here, because this is what we got out of this, right? So that's just as good. All right, so now that's as far as approximating those values. Now, let's talk about the remainder of a Taylor polynomial, because what we want to know is how accurate are our approximations, right? I mean, in this case, super accurate. But let's see. So let's talk about something called the remainder of a Taylor polynomial. And this is what we have. So Taylor's theorem. So Taylor's theorem says if a function f is differentiable through order n plus 1, so in other words, we can take n plus 1 derivatives on an interval I containing c, then for each x in I, there exists some z between x and c such that f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. Keep going with that pattern, right? Plus the nth derivative of c times x minus c to the n over n factorial plus r sub n of x. And here that r sub n means our remainder. So in there we can figure out just how far off we're going to be able to be. So in here, where r sub n of x, and again it represents a remainder, is equal to the nth derivative evaluated at c times x minus c to the n over n plus 1 factorial. Alright, and in here, essentially what this 0 represents is how accurate do we want our stuff to be, all right, or how close do we want to be to the actual value of C. So let's see. Example D. So find the third Maclaurin series for f of x equals sine of x. All right. Use the result and Taylor's theorem to approximate sine of 0.1, right? And determine the accuracy of the approximation. All right. So find the third Maclaurin series for f of x equals sine of x. All right. So let's do that first. So we had our function of x was sine of x. First derivative, f prime of x is cosine of x. Next derivative, f double prime of x, well, the derivative of cosine is negative sine. The third derivative, the derivative of negative sine, is negative cosine. We're evaluating this at, well, it says Maclaurin series. Maclaurin series is where our center is 0. So we're evaluating this as 0. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Cosine of 0 is 1, but with the negative in front of it, we get negative 1. So what do we have now? Well, let's see. Our third polynomial, our third Maclaurin polynomial, is going to be, well, I'll write down the formula. F of 0 plus f prime of 0 times x minus, well, just x, right, because we're doing Maclaurin. So x to the n, x to the 1, plus f double prime of 0 times x squared over 2, plus f triple prime of 0 times x cubed over 3. In this case, well, what was f of 0? F of 0 was 0, plus f prime of 0, 1. So I have 1 times x, plus f double prime of 0 is 0. So 0 x squared over 2 factorial, I forgot the factorials, plus f triple prime of 0 is negative 1. And then we have x to the third over 3 factorial. So we can actually reduce this now to say, well, the zeros go away. So I have x minus x cubed over 3 factorial. 3 factorial is just 6. So there we go. We found the third polynomial, the third Maclaurin polynomial for sine. Now, what was the rest part, the next part? Approximate sine of 0.1. Okay, so in here, sine of 0.1 would be our p sub 3 of 0.1, which is, well, 0.1 is 1 cent. So p sub 3 of 1 cent minus, let's see, p sub 3 of 1 cent is equal to 1 cent minus 1 cent cubed over 6, right? And at that point, we say, well, 1 cent cubed is 1 1,000. So I have 1 cent minus 1 1,000 over 6 is 1 6,000, right? And then common denominator there, well, that would be 6,000. To go from 10 to 6,000, multiply by 600. So we have 600 minus 1 being 599 over 6,000. And well, that is approximately, if you put that into the calculator, it would give you 0.0998 with 3 repeating. All right, 0.9983 with 3 repeating. Cool. Next part. Determine the accuracy of the approximation. So how close is our approximation? So that's where we're going to be using this formula up here. And perhaps I should copy this. So here's what we're going to say. This part right here, what we're trying to figure out is, well, what would this actually yield? So to figure that out, well, first look at this. We need the n plus 1th derivative of f. And what is that? Well, in here we went up to the 3rd derivative, right? So we need to figure out the 4th derivative. So in here we have the 3rd derivative being equal to negative cosine of x, right? So the 4th derivative, that's our n plus 1th derivative. That's going to be, well, the derivative of negative cosine is, positive sine. And, well, alright, so now, our remainder, well, how far off are we? So, our remainder should be bigger than 0. So, right, so here we have our remainder. I'm putting that sub 3 there because our Maclaurin polynomial was based out of the 3rd Maclaurin polynomial. And that's going to be, well, the n plus 1th derivative evaluated at z. So I'm going to get just sine of z over n plus 1 factorial. What was n? N was 3. So over 4 factorial times, well, x minus c. C was 0 because we were doing Maclaurin. So we have x to the n here is now 3. All right. This should be to the 4th. And this should be to the 4th because this should say plus 1 here. Oh man, did I copy that? Did I write that wrong up here? I did. This should be n plus 1. Alright. So now, at this point, well, what do we get? This piece right here. Let's consider sine of z, right? Since we're just trying to consider positive values, right, because we want our remainder to be positive, well, we know that in general, sine of z is less than or equal to 1, right? So what this tells me now is that if I replace the sine of z, I can say that this entire thing is less than or equal to x to the 4th over 4 factorial, right? And now that we've got that, we can say now that r sub 3 of x of 0.1, right, because we're trying to figure out 0.1, that would be, well, less than or equal to 0.1, which was 1/10 to the 4th over 4 factorial. 1/10 to the 4th is 1 over 10,000. 4 factorial, 4 times 3 times 2 times 1 is 24. So 1 over 10,000 times 24, so we have 24, and then 10,000 is 4 zeros. So that means that we're within that much of an error. As a decimal, this is approximately 0.000004. That's how close we are on our answer. Alright, so in other words, let's see. What we're saying here is that sine of 0.1, it is going to be at least the value that we approximated, which is this thing, 0.9983. And I think I said that wrong, 0.09983, with the 3 repeating. And it's going to be under adding this much to that. So that's going to be 0.09983 repeating plus 0.000004. In other words here, what we end up with here is between 0.09983 repeating and, well, 1, 2, 3, 4, 5. So 0.1234 5. In other words, oh no, hold on. That was wrong. So it's a 3, and then I need to add that 4 to the fourth value here, right? 1, 2, 3, 4, 5 zeros. So this becomes a 7 there. So that's somewhere between those two. And in fact, sin of 0.1, if you plug it into the calculator, it will give you 0.099834. So we are actually pretty in a pretty close estimate, right? Between the two. So there we go. That's the end of 9.7, which again were Taylor polynomials and Maclaurin polynomials, and using them to approximate different values. Cool.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.